one.
All right, welcome back. If you guys need the free body diagram, Brian, go back to the last video and look at the end of it. And if you need to see how we got to here, go look at the last video at the end. So right now we were calculating KE1 plus work of friction equals KE2. And so we're just going to do the math. So we've got over here, this is 20 and 15 squared is 225. So 20 times 225 is 450, 4,500. Plus W friction is going to be equal to half of 40 is 20, 10 squared is 100, so 20 times 100 is 2,000, which means that the work of friction is 2,000 minus 4,500, or negative 2,500 joules. Not 2,500, negative. All right, so that's also happens to be the work, total work done on him, because if you looked at the free body diagram before, it was gravity going down, normal force going up, and both of those are perpendicular to his motion, so those don't do any work. The only thing that was parallel to his motion was force of friction. So the next part is asking us what's the force of friction acting on him. So we use our good old W equals F parallel times D. And the work is negative 2,500. And that's 25,000. And that's equal to the force of friction times the displacement. The displacement was 30. And when you divide that, you get that the force of friction is equal to a negative 83.33 newtons. All right, and then the last question is asking about the coefficient of friction between his skates and the ice. So we're going to use F friction, and I'm going to do it right this time, equals mu times normal force. Okay, our force of friction, we're going to use the absolute values of those, 83.33. It's going to be equal to mu times normal force. Normal force was 400. So we're just going to divide those out. So 83.33 divided by not 400 is 0.208325. So we'll just say mu equals 0.208 is fine. And there's no units on that. And that's done. All right. Here we go again. So here's Julie driving her race car at 50 meters per second on a wet concrete roadway. She hits the brakes and she skids. So hitting the brakes and skidding means that's going to be force of friction that's slowing her down. And then she collides with the wall, and it gives you the coefficient of friction. So here we go. Here's our free body diagram. We've got Julie. Her force of gravity is 1,000 times 10, which is 10,000. Which makes sense. Well, not her in the car. So this is 10,000. Oh boy, this is messy. I'll just sneak another zero in here, actually. Newtons. All right, normal force. Same thing. Again, she's on flat ground, so that's why her normal force and her force of gravity, and nobody's pulling her up or pushing her down, so that's why her normal force and force of gravity are the same right now. And then the only other thing, because there's no applied force here, she's slowing down. The only other thing that's doing work on her is force friction. And that's here, and we don't know what it is yet, but we will figure it out really quick. Because we know, that force of friction is equal to mu times normal force. And we happen to have our force of friction. Well, we don't have force of friction, but we have our mu of 0.55 and our normal force of 10,000. Okay, so which that means force of friction is equal to, so we move the decimal over 4, so 5500. It's going to the left, but that's what, so negative 5500, doesn't matter. Okay, the last one is how fast was the car going when it hit the wall. This was challenging for people because of one simple error, pretty much. So we've got our good old E1 plus W equals E2. And we're just talking kinetic energy. So our E1 plus our work of friction is equal to our KE, 2. I only include a work of friction. That's the only thing that is parallel. Just put that number up here. There we go. Okay. So our KE, what we're going to do is we're going to do 1/2, not 12, 1/2 of 1,000 times 50 squared, which is going to be some huge number, plus our work of friction, which is force of friction of, so I'm going to put a negative out because we know work of friction is always negative. So our force of friction is 5,500 and our D displacement is 100. And that's going to be equal to 1/2 of 1,000 times our V2 squared. Okay. So over here, we've got 1/2 of 1,000 is 500. 50 squared is 2,500. So 2,500 times 500. I'm going to use the calculator for that. 1,250,000. 1,250. Okay. Then we have to subtract 5,500 times 100. So that's 550,000. Boom. And that's equal to 500. Oops. V2 squared. Okay. Over here. So we get 700,000 on this side, I think. That doesn't seem right, but whatever. Equals 500 V2 squared. So I'm going to do that 700,000, which I'm like not real sure about, but I'm going to divide the 500 and I get 1,400. That seems right. So 1,400 equals V2 squared. Then I'm going to take the square root of 1,400. Oh, for crying out loud. I hope it's the answer. I think it is. Here we go. Yeah, it is. So 37.42. Whoa. Do I see that? So V2 equals 37.42 meters per second. And we know that's right, or we can think that's right, because she hit the brakes. So if she was starting at 50 and she got down to 37, that makes sense because she hit the brakes. By the way, that's super fast. Okay, here's the next one. We're going to be doing this free body diagram. So Joe is really push. I know. Everyone's like, it's pushing. I know. Pushes Katie at a constant speed. Woohoo! F9 is 0 in her sled as shown. So here we go. Here she is. Katie and her sled weigh 60 kilograms. So that means that her force of gravity is going to be 600. Now here's the thing. There's other vertical forces other than just normal force and force of gravity. Because when you look at Joe, he's pushing her down and to the right. So we've got 100 newtons of his force going down. It doesn't even look like a G, that looks like an S. So I'm going to put F Joe, and that's going to be 100. The other thing I'm going to do is I'm going to put, what a pain in the neck, you guys. 100. The other thing I'm going to do is I'm going to include this part, the 240. So this is also FJ. I would call this FJX and that FJY. I'll add the Y down there in a second. That's 240. I don't include angled forces on my free body diagrams because it is more confusing that way. And this makes it easier to balance. So, whatever. We're just drawing things everywhere. So, next we're going to do normal force. Normal force has to balance out going up. And we've got 100 plus 600. So, this is 700. Ooh. That's my normal force.